In this class, I wanted to start discussing about TCP's congestion control. So what exactly is the problem here? So we have a sender who is communicating to a receiver via TCP. And let's say the data is going through many routers along some path. So if we zoom into one of these, suppose there is an output queue over here. So packets from here are going to go through the network and they may enter some queue over here. Now it's possible that lots of data comes in, maybe from different input links, and goes into this queue, because of which the queue fills up. And that's a problem, because first of all, what can happen is that packets can get dropped if the queue is full. So when congestion occurs, the following problems also exist. One is that packets get dropped, and routers will not retransmit them if the packets get dropped because of a queue being full. Right? The router has just run out of space; it can't do much. So this is a problem, because it will require retransmissions from the source. And secondly, we face excessive queuing delays. So we know that round trip time, or even just the one-way delay of packets, the time taken for a packet to go from here to here, is the speed of flight delay plus the transmission delays at each of these routers. That's because of the store and forward process. But in addition to that, you have queuing delays. So if you have large queuing delays, suppose many of these routers even are congested, the router queues are congested, the total delay is the sum of these queuing delays in addition to the minimum delay that you see on the path. And that can affect the performance of some applications. Suppose you're doing a voice over IP, or sort of Skyping or something like that. You're talking to somebody over the IP network, and those packets are going over here. So they will also face these queuing delays. Okay, so maybe you don't care about queuing delays much if there's a file transfer, but if there's some delay sensitive application, it can matter. So just to be more clear about it, so suppose there are packets coming from TCP and in addition, let's say that somebody is using UDP, let's say, and maybe he's doing his voice call over UDP. So the voice information is encoded and put in packets, and let's say it's going over UDP, and let's say voice over IP application. And both of these, let's say, enter the same queue. There is no priority queuing or anything done to differentiate between these. So as it comes into the same router, so I'm saying this is the same router. These could be on the same input link, or they could be on different input links, but they're meant for the same output link, so they get dumped into the same queue. So some of these may be UDP packets, but the rest may be TCP. So there is congestion, we are saying, and this queue is pretty much filled up. So there is a problem for this voice over IP traffic, because these packets have to also wait in the queue behind the TCP traffic. So in general, in a router, you'll have all sorts of applications all mixed up together. The packets go into the same queues, And maybe some applications are sensitive, they care about the delays, but some are maybe tolerant to the delays. But overall, large queuing delays are a problem for certain applications. So we would like to keep the queuing delays low if possible. Okay. So these are two issues that we face, and of course if the application needs reliable data transfer, you would have to retransmit these drop packets. So how does a TCP application know whether there is congestion or not? TCP is running from here, right? And you're sending data and you're getting back acknowledgements. We said that these intermediate routers don't collaborate with TCP. At least in this course, we are not going to consider specialized mechanisms like ECN, which I mentioned in the last class. So here we assume that the router just tries to put any input packet into the appropriate output queue, and this is just a FIFO queue. It's emptied out as soon as possible. It's emptied out, and the packets are sent out at the link capacity. We said that TCP uses something called a window. Just recall this, and window is, we said, the minimum of advertised window. This is for the flow control, and then there is the congestion window. And this advertised window takes care of the flow control, and this takes care of the congestion control. Congestion control refers to trying to reduce the congestion that takes place at intermediate routers. Let's think for a moment how, if you were to design TCP, you would solve this problem. So what sort of signal information do you have? You're sending out some packets and you're getting back acknowledgements. So what can you really infer about the network from this? So we are just sending packets and getting back these ACKs. Can you say if there is congestion occurring? So let's think for a moment. Suppose I plot RTT over time. This is the time at which packets are sent. So let's say data packets are sent out, and this is the observed RTT. So we said that typically you will see something like this. You will see a minimum delay, and on top of that you will see some increase or decrease. So can you look at this and tell me if congestion is occurring or not? And one obvious thing which comes to mind is that when the RTT is high, that's probably due to queuing delay, and that's a signal of congestion. So maybe this could signal congestion. So this may be one way to do it, but how exactly would we do this? This minimum delay could be very different for different TCP connections. So possibly we could subtract out that minimum delay and then focus only on the queuing delays. And then the question would be like, should we put some sort of a threshold or what? If the queuing delay is above a threshold, should we say there is congestion? Something like that, right? We'd have to do something like that, but we have to do it correctly. And probably we want to again smooth out this round trip time, because like last time in the last class we were discussing, there could be a sudden spike. You never know why a packet could be delayed. Maybe there's something besides queuing delay too. The router was just busy for some other reason and it couldn't forward the packet immediately. Whatever could have happened. So just a single packet having a large round trip time may not be a good signal for congestion occurring. Maybe it should happen for a few packets. So we'd have to smooth this out in some way, and maybe based on that we have some sort of a threshold which says that there is congestion or not. But it's not clear what to do, because if the links are fast, like suppose you have a 10 gigabit per second link, actually maybe even a large queue, suppose you have a queue, let's say of 1 MB, okay, that's a reasonable buffer size, it can hold several packets. But suppose this queue is being emptied at rate C bits per second. So this would be, what is 1 MB? It's 8 megabits. Right, and so how long would it take for this queue to empty? Divided by C, this much time. And you can see that if this is in like tens or hundreds of even tens of gigabits per second, the time for such a queue to empty, which is effectively the queuing delay, is going to be quite small. Right, so if you have, of course, a megabit per second, then of course it's going to take 8 seconds. But if you have a gigabit, it's going to be what, 8 milliseconds. So this is going to get smaller and smaller and smaller the larger C is. So it's a tricky thing. I mean, if I have an absolute threshold, maybe I will not sense queuing delays at all. You know, the queuing delays might actually be very small for high speed networks. Okay, so I'd have to sort of look for slight increases in the queuing delay, and maybe that will signal that there is congestion. So it's not non-trivial to put a threshold over here, because in some cases, I mean, the queuing delay may never exceed that particular threshold. Especially when you have, let's say, a reasonably high buffer size, but this data emptying rate is pretty high. So anyway, we'll have to look at this, but this is one way we could look at delays. And what other information do we get? So the other information that we get is packet loss. And of course, the intermediate routers don't tell you explicitly that they have dropped the packet, but you can infer that a packet loss has occurred, for example, using a timer. So we said anyway we are using timers. If a packet is lost, I don't get an acknowledgement before the timer expires. I say that it's gone, and of course I try to retransmit it. But in general, we can use different techniques to detect packet loss. And one, of course, the idea that I just mentioned is you use a timeout. But there are other methods too, because the receiver is sending you feedback information through acknowledgements. So it's possible that you can get some information from that. So let's say we use ACK feedback to infer losses. So I'll give you the basic idea. Suppose this is a packet number, and just let's say I have these are the packet numbers 3, 4 and so on, and I'm going to get back acknowledgements. Suppose these are ACT. What does that tell us? So we'll see that TCP doesn't exactly do this. It uses a slightly different mechanism, but suppose, just for a discussion's sake, it is sending back an acknowledgement for packet 1, for packet 2, 4, 5, 6 and so on, but you don't get back an acknowledgement for 3. Okay. So instead of waiting for the timer for this 3 to expire, we could just look at these acknowledgements, and we can say, you know, that 1 and 2 reached, 4, 5, 6 reached, probably 3 was dropped. You know, why would the acknowledgement of 3 not be coming back? So we might infer that 3 is dropped based on this. But somebody might argue saying, how can you say that? Maybe the packet reached but the acknowledgement was dropped, or maybe just the acknowledgement is delayed, or the packet was delayed somewhat, and you need to wait for a certain amount of time. So those are valid arguments, and so we have to make a good decision, and we'll see what TCP does. So researchers have sort of concluded, they propose some mechanism which has sort of become the default, and we'll see how exactly they infer that a packet loss has occurred just from acknowledgements coming back. So these are two mechanisms: either you infer congestion from packet loss, or you infer congestion looking at the queuing delays. So let's go through the basic mechanism of what exactly TCP does. Let's see what exactly the sender does. So this is the sender, and suppose this is a buffer at the transport layer at the sender. So this is the beginning of the buffer, and let's say that the application is writing to this particular buffer. So let's say this much has been written. So the application can always write more and more data. It doesn't have to send it at one shot. Right? So if, for example, you're typing away, every time you type in a particular keystroke, that is converted to an appropriate code word, some ASCII code, and it's sent out. Right? So it's just dumped into this buffer, and then it's the job of TCP to send it out. So what is the sequence number going to be? We said that the sequence number doesn't start from 0. Let's say we start from some X over here, right? So the first byte, let's say, is X, okay? Or if you're using X for the SYN packet, then of course that is counted as 1. So let's say that, suppose X corresponds to the SYN. Then this would be X plus 1, the first data byte. So suppose this much amount of data has been dumped in initially. So what is the sender going to do? It is going to try to send out data, and it's going to divide this up. So the maximum amount of data it can send out in a particular segment is called the maximum segment size. So we don't want to send more than that in a single packet. And the question is, initially, what should I do? Should I send one segment or two segments, or what? And of course, the answer really depends on what your window size is. So suppose my window size was initially this much. So we've assumed that the SYN handshake is over, right? SYNAC and so on, right? That's all done. So suppose the window is this much, then I'm allowed to send out this much into the network. None of this is acknowledged, remember, and the window corresponds to the maximum amount of data that you could have sent out, which is not acknowledged. So let's suppose that the window size was 3 initially. Window size corresponded to 3 MSS, okay, and in which case you could send out these 3 packets. So if initial window is equal to 3 MSS, so we send out 3 packets, let's say just 3 segments, and each segment would go on a separate IP packet. So the MSS of course is set appropriately by the OS. It would be a little bit over 1,000 bytes, so around 1,500 bytes. So okay, so this is what we would do initially. If my window size was 3, I could send this out. So what happens after that? So we have to look at the receiver. So the receiver initially has its own buffer, and that is empty. So here to the sequence number is x plus 1. So we are assuming that the sender is sending this data to the receiver. Of course, it's a full duplex connection, so the receiver could have its own buffer, right? I mean, it could be that this node is the sender sending over here. So we are ignoring that. We're just looking at the one-way data transmission. So right now, what would have been sent out in the acknowledgement? So the SYN packet had X as the sequence number, and SYN had its own, this one had Y, let's say, but the ACK had X plus 1, right? And then of course you had an ACK this way too, Y plus 1. So what was this saying? This is saying that I got sequence number X, which corresponded to the SYN packet, and I'm expecting X plus 1. So he is saying the next byte that I'm expecting is X plus 1, this first data byte. Okay. So these 3 segments, so the first segment will have X plus 1, as its sequence number. This is going to be what? It's going to be X plus 1 plus MSS bytes. So the sequence number and ACK number corresponds to the byte number. And what would this be? This third one, it's going to be X plus 1 plus MSS plus MSS. So when you send out these segments, this is the sequence number that you would include for each of them in the TCP header. So what if the first sequence number or the first segment actually reaches the receiver? So let's write that. So suppose this one comes here. Now the receiver sends an acknowledgement for this. And what is it going to send in the acknowledgement? It is going to say that I got this last byte, and it's going to tell you what is the next sequence, what is the sequence number of the next byte I'm expecting to receive. So ACK for this has ACK number equal to X plus 1 plus MSS. Because it got the full segment, it's saying that this is the next byte that I'm expecting. So this ACK is saying that what I expect is this first byte of the next segment. And now let's say that this, so first let's say suppose this ACK reaches the sender, then what's going to happen? So previously the last ACK byte was what? It was the last ACK number was x plus 1. Let's use a different color. So initially the ACK number was here. It was x plus 1. So this was saying that I got everything up to x. Now the ACK number has shifted over here to x plus 1 plus MSS. So this is telling the sender that I have got everything from the beginning up to x plus 1 plus MSS, and I am expecting x plus 1 plus MSS. And this is something called a cumulative ACK. So that means if whatever ACK number, some particular ACK, let's say ACK number Z is sent in a particular ACK, this implies everything from the start till Z minus 1, till byte Z minus 1 has been received. So fair enough, so we've got this particular segment, so we are sending that particular ACK. Now what can we do over here? So the window is saying that the amount of outstanding data is whatever that's really should be upper bounded by the window. And just see this, so I've got this data. Initially I could only send from the beginning this much data. Now I know that the receiver has got this, so I can actually push this window to the right. So this is the window after the first acknowledgement. So this is good for us. I could push the window to the right, which means I can also send out some more data. I can send this data out now. So just to recap, initially my window size was 3 MSS, so I just sent it out, but then that was the maximum I was allowed to send out, the maximum unacknowledged data. I got back one acknowledgement, so I pushed the window to the right and I was able to send out another packet. And this mechanism, this is called a sliding window mechanism. The window slides more and more to the right as I get more and more acknowledgements. Okay. So here of course I am assuming that the window size is the same, but when we are doing congestion control we can increase or decrease the window size. If we find that there is a congestion, then we are going to decrease the window size, but if there is no congestion we can even increase the window size. Okay. So it may happen that if you increase the window size you can send more than one packet out. That may happen. So this is the mechanism that's going to take place. So you might ask a question like, what if this second packet, let's say, was lost? Okay, the first packet reached, and of course the fourth packet was sent out because the window shifted to the right, but what if the second packet was lost? So let's say that this was lost and the third one reached. What acknowledgement are we going to send out for this? So we said in TCP we are going to send out a cumulative acknowledgement. So this is going to say that everything, I got everything from the start till the acknowledgement number over here. And I did not get this data, so I can't put any acknowledgement number larger than this x plus 1 plus MSS. Because that would be lying. It would say that I've got this information when I haven't. So what TCP does is that even when this third packet reaches and this one is dropped, I will send back an acknowledgement, but I will put the acknowledgement number as x plus 1 plus MSS. So ACK number is still x plus 1 plus MSS because we are using this cumulative ACK rule. Okay, so if there's a missing packet somewhere because it's dropped, or maybe this could be delayed for some reason, and in that particular case I will still send up acknowledgements. I'll keep sending acknowledgements for every received segment, but I will include the acknowledgement number only up to the continuous, the maximum location in this buffer where I have received everything before it, okay, where there is no missing information. So even if this particular fourth one reached, then I would send the same acknowledgement number. Right, and these acknowledgements which have the same acknowledgement number as a previous acknowledgement which was sent are called duplicate acknowledgements. So duplicate acknowledgements would look identical to what you had over here because ACK number is the same. So that's why they're called duplicate acknowledgements, but actually they convey some information. They are telling you that I got one more segment. So of course the drawback is that I don't know which segment that I got. Right? Was maybe this third one was also lost and I got the fourth one. Okay, but so when an acknowledgement was sent for this, you don't know which future packet is it for among those which you sent out. So duplicate acknowledgements have ACK numbers of some previous ACK sent out. And they convey that information about that one more segment was reached. They don't tell you which one, but they tell you that I have received one. Okay, so in this particular case, ACKs were sent for these three. So we definitely know that this one was received because the ACK number has gone to 1 byte after this particular segment. But these, if I get 2 more ACKs, it's telling me I got 2 more segments, but it's not telling me which of the future ones that I sent out I got. Okay. So it tells so I should say that each dupack says that one more segment was received. But it does not tell me which segment explicitly. Of course, you can try to be clever and try to figure out which of these were received. But in a general situation, you won't know for sure. Okay, so you also have to be a bit careful because it may happen that some intermediate router might, due to some weird reason, it might replicate a packet. So maybe it got one, it was supposed to forward the acknowledgement and it sent it out twice. It's something tricky like that could happen, because of some misconfiguration. So you have to be a bit careful in using these dupacks. But assuming that no such funny thing happens, this is what we do, and each dupack indeed conveys that one particular segment has reach the receiver. So this is the basic window mechanism. The window slides to the right. So whatever is your last acknowledgement number, beyond that you are allowed to send window amount of bytes into the network. So in this particular case, even though we got back these duplicate acknowledgements, we couldn't push the window further to the right. So what we normally have is that if this is the last acknowledged data, this is the buffer, at the sender, you are allowed to have window bytes beyond this which have been sent into the network. And if you get duplicate acknowledgements, you can't in general push this to the right, because the duplicate acknowledgements are still giving you this particular acknowledgement. Okay. So this is the sliding window protocol which TCP uses. First we will discuss some of the principles of congestion control. So once we've discussed these main ideas used, we'll see how they are put together in different TCP protocols. So first principle is to be conservative in increase of congestion window in case there is no congestion. If there is no congestion, increase congestion window conservatively. So what does this mean? So remember that the data rate at which you are sending into the network is essentially your window divided by the round trip time. This is roughly what it is. And recall that the window is minimum of advertised window and the congestion window. So for now we will assume that window is equal to congestion window. Let's assume that the advertised window is large. Okay. So we are assuming that there is no need for flow control right now, that the receiver has a lot of resources. So one of the things we have to decide is, suppose there is no congestion, we are looking at whether there is packet loss or whether there is, let's say that the round trip time has gone up, right? And those are the two methods to find out if there is congestion. So suppose there is no congestion, then how should we increase the window size? Because after all, we want to use up whatever resources are there in the network. If we have a 10 gigabit per second link, then why not use it? Why send at 1 megabit per second when you have 10 gigabits per second? So we want to increase the window size so that we efficiently use up all the resources available. But we want to do that in a conservative fashion. We don't want to be too aggressive in increasing the window size. So what researchers have suggested over the past is to do what's called an additive increase of the window size. What this means is that if I plot window size against time of a particular TCP connection, let's say I'm plotting the congestion window, suppose there is no congestion detected, the window size should increase in an additive fashion over time. Okay, so it should be like a linear increase like this. And so we are not being too aggressive. So you might say, what else could we do? I mean, you can have an exponential increase or super exponential or whatever, right? But here, even though there is no congestion, there's no packet loss or RTT hasn't increased a lot, I don't increase by too much. So the idea is that you increase by increase the congestion window by one maximum segment size per RTT. So this is a slow increase. We are not being too aggressive in increasing the window size. And we'll see that when we actually have packet loss, we will decrease the window in a drastic manner. Okay, so how is this additive increase implemented? This might look very straightforward, but it's tricky because what is the RTT? I mean, the RTT that you measure varies a lot, and it depends on so many different factors. So I mean, if I knew some sort of an RTT, I could have a timer and increase the window size by 1 MSS every RTT. But TCP uses a different mechanism. TCP uses a self-clocking mechanism where every time you get back an acknowledgement, I increase the window size by a certain amount. So TCP uses self-clocking. So I don't have a timer or actual clock to increase this window size. I use the returning acknowledgements as a sort of timer to increase my window size. So every time an ACK arrives, we increase the window. So suppose congestion window is CW, and let's say that maximum segment size is MSS. So this is a number in bytes. So what are the number of packets, number of segments which I have sent out? So I'm assuming the CW is let's say a multiple of MSS, just to simplify things. So the number of segments is equal to congestion window divided by MSS. So I'm going to get back this many acknowledgements in one RTT. Okay, so what this means is, so if CW is my window size, I've sent out this many data segments. Okay, so the number of these is given by this. And what we are saying is that every time an acknowledgement comes back, suppose an ACK comes back for this, we are going to increase the window size by a little bit. So when each of these comes back, I'm going to change by a little bit. Okay. Of course, you might think there may be other ways to do it, that you wait for all of these to come back and then you increase it or something like that. But that's harder to get working because some acknowledgements may be lost, and then what do? You have to wait for all of them to come back or what? So what the TCP designer said is, effectively we want the window size to increase by 1 every round trip time. Okay, so roughly this is 1 round trip time, and I want the window size to increase by 1. So I increase not by 1, I have to increase by a smaller amount for each of these acknowledgements coming back, so that effectively at the end of this, after the third act, let's say, okay, so I'm assuming that congestion window is 3 MSS over here. So over here I would increase the window size by 1 MSS. Okay, maximum segment size is essentially the size of one segment that you send out. You would normally want to send out the largest size possible, just to reduce the overheads and things like that. Okay, so every time you send out a TCP packet, a TCP segment, there are overheads at all the different layers, right from physical layer all the way up to the application layer, or at least the TCP layer. And so that's a waste. So I mean, all that overhead is constant for each particular segment. So this is the actual application data that you're sending out in a particular packet, and these are all overheads from headers. So I want to keep these the overhead small compared to the amount of data I'm sending. So the larger I have, the larger the packet I send, the more data, so the percentage of overhead goes down. Okay, so normally TCP would send the maximum sized segment if possible. So how are we going to increase the window size so that effectively we increase by 1 MSS? So there are this many segments which I've sent out over here, and effectively I want to increase by 1 MSS. So the number of acts that I am getting back is also going to be equal to this. So per act, how much do I want to increase the window size? So I want to increase by MSS divided by number of acts which are outstanding. Okay, so I've sort of simplified things. In practice the situation could be much more complicated, but here I'm saying I've sent out the full window in one shot with these 3 packets, and then I'm getting back the acknowledgements like this. Okay, in practice it may happen that you get back an acknowledgement even before this third one was sent out. Okay, I've simplified things. So this number of acts is saying that for that particular window which I've sent out of packets, how many acknowledgements do I expect back? So this is the number of segments in the window, number of acts coming back in the window. Okay, and so what is this going to end up? And so intuitively this is clear, but we'll see the formula that we end up with will look a little bit weird. So we have this, which is equal to MSS square divided by the congestion window. It seems a little bit weird. Every time an acknowledgement comes, we increase by this amount. So this is what TCP does, and it doesn't exactly give you an increase of 1 per round trip time. It actually turns out to be a little bit less than that, but effectively that's what is done. Okay, so what is the additive increase rule? On receiving an ACK, what you do is congestion window is increased by MSS square divided by congestion window. So congestion window is not constant. Every time you get an ACK, it increases by a little bit. Okay, and roughly that we end up by almost increasing the congestion window by 1 every round trip. So we are assuming that there is no congestion when we are doing this. Okay, so we think there is no congestion, so we are slowly increasing the windows. So a second principle is that if there is congestion, we drastically decrease the window size, okay, just to be more aggressive. We don't want to congest the network, we want to relieve the network of congestion, so we drastically reduce the window size. So if congestion is detected, decrease window size aggressively. So what have we looked at till now? We are saying that if there is no congestion, this is the window, this is the time, we increase slowly, this additive increase manner. But suppose congestion is detected, you might say, should we just in a similar manner decrease the congestion window by 1 every round trip time? That seems logical. If I'm increasing it a little bit when there's congestion, why shouldn't I also decrease it in the similar manner? But that could lead to problems. So the thing is that these queues are getting filled up. If you have different flows coming in and the queues are filling up, and we detect congestion, let's say because of packet loss or something like that, so the network situation is really bad now. Packets are getting dropped left and right at some router. So you want all the TCP flows to back off so that this queue empties quickly. So using ideas from control theory and so on, where control theory is a subject where you look at stability of systems when you have a control system with feedback loops and so on. So using the ideas that the researchers had at that time in the 80s, they said let's be aggressive. So when we detect congestion, we don't additively decrease, but we are more aggressive. So for example, you decrease the congestion window all the way up to 1. That's one way to do it, and otherwise some people suggest that at least you make it half. Okay, so these are the ideas that were proposed. So initially there was a TCP protocol called TCP Tahoe, which actually used this drastic decrease to congestion window equal to 1. Okay. So there are various TCP flavors, and since I suppose some of the researchers were based in California, they gave it names like Tahoe. So these are all very picturesque sort of places in California. I've been to Lake Tahoe, a nice skiing place in winter. Okay, so Tahoe, Reno. So these are various protocols. So as they change some of the rules, they give it a new name, and TCP Vegas and so on. Right. So some of my colleagues at Rice University came up with something called TCP Africa, which also did quite well actually. Okay, I think it has many citations. It came out in a good conference and so on. Right. Anyway, so TCP Tahoe essentially sets congestion window equal to 1 on detecting congestion. And Reno essentially decreases the window size by half. So these we will not study in this course, it's quite advanced. But TCP Vegas we will look at a little bit later. So this is called multiplicative decrease. So you increase the window additively. That's an additive increase. It's not constant slope. But you have a multiplicative decrease. Here we are multiplying by a factor of 0.5 to decrease the window when you have congestion. And people have shown, and of course experimentally also you can observe it if you do a simulation, let's say in NS3. You will see that this will help the queues relax fast. Okay, so everybody slowly increases their windows, and then of course at some point the input rate is going to be greater than the output rate of this queue. So the queues fill up, but then when you see packet losses, different flows see packet losses, they drastically decrease the window sizes so that this queue will eventually decrease. Okay, so we want the decrease to be quite soon, so that congestion is not there in the network for very long. So this is another principle. So when you look at TCP papers, you may see something like AIMD. So this stands for additive increase, multiplicative decrease. And usually TCP protocols will implement this idea. So let's move on. So let's look at a third principle. And so one thing we haven't discussed is how do you find a reasonable window size initially? So the issue is that suppose this is the sender, or this is the sender, let's say, and this is the receiver. What is the data rate that you can send out? What is an appropriate window size? And so suppose this is 10 gigabit per second, and the round trip time, let's say, is 0.1, let's maybe take an example, let's say 1 second. Okay, so suppose the round trip time is quite large, and your initial window size is, let's say, only 1 MSS. Which roughly, let's say, is 10,000 bits. Okay, so suppose 10,000 bits. So what is our initial data rate? It's 10 to the power of 4 by, this is really large, 10 to the power of 10. I beg your pardon, sorry, we need to divide by 1. So it's only 10 to the power of 4 bits per second, when what you can get here is 10 to the power of 10 bits per second. So there's a 6 orders of magnitude difference between what you're initially getting with the TCP window size set to 1 MSS and what you could be using. So I mean, in theory, you may be the only person using this link, and you have a large file. So think about it, if you're doing additive increase, how long is it going to take us to actually transmit this file? So you have, let's say, 1 gigabyte or something like that, and in theory, if you were using all the data rate over here, all the link capacity available, you would be able to send that in a jiffy, within a second or something like that. You would be able to send the whole file across. Okay? Whereas now you're starting only with 10 kilobit per second and you're increasing it by 1 MSS every round trip time. So it could take you minutes or even hours to transmit this file, even though it could be sent, let's say it's a 1 GB file. Even though it could actually take you only just 1 second if you were using the resources efficiently. So additive increase in the beginning is not good. So you have to start with a low window size because you don't know what this is initially. You don't know who the receiver is, you don't know much about the path when you start up. So initially you always want to have a low window size. Okay, but additive increase is too slow in some situations, so we want to be more aggressive. So initially set window size small, since we do not know the appropriate window size. Since we do not know the appropriate, let's say the data rate at which we should send into the network. So we are being conservative over here. Right? We don't want to congest the network by having a very large window size initially. Okay. And remember that the data rate also depends on the round trip time. So 1 ms could also be a high data rate if the receiver is just next door on the same LAN or something like that. Okay. So we don't know how this window size is going to translate into a data rate, and we don't know what is the capacity of. So we'll start slow. We start with a small window size, but at the same time additive increase is maybe too slow. So what do? We want to be aggressive. So what we will do is that we will have an exponential increase. So this is only done when you start the protocol. Of course, the fine details we'll look at later on, but the idea is that you want to do this initially. It may happen in certain situations that even later on in the protocol you have to again aggressively increase the window size. Okay, but what we want is at least that initially we are aggressive, though we start with a small window size. So what was suggested is exponential increase. So initially, the congestion window, let's say, is 1 maximum segment size, and for every round trip time, what we are going to do is we are going to double it. And 8 MSS. So we increase the window size in this fashion, really fast. Of course, we can't do this forever because then we're going to end up congesting the network really badly. So we'll see what we do in a moment. But initially we do this, and the question is how to implement this. And again, we don't want to have a timer which measures the round trip time and so on, for the same reasons mentioned earlier. So we are going to use self-clocking. So we want to double the window size. So the number of acts in a window we said is congestion window divided by MSS. Okay. So this many acts are coming back, and we want the congestion window, we want to increase the window a little bit at every act, and for this many number of acts we want the window size to double. Okay, so how do we do it? So per act, so this is all done at the sender. So every time the sender gets back an acknowledgement, we increase the window size by 1 MSS. Okay, so that the total increase for this many acts is how much? So we're getting this many acts and we are increasing the window size by MSS for each one of them. So roughly we are increasing the window size by the window size itself. So effectively we will be doubling the window size. Okay, so of course I'm assuming that the congestion window is constant and so on, which is not true. We are increasing by a little bit every time. Right, but I think that argument doesn't hold over here. Sorry. So we will indeed increase by this much, pretty much in the window time. Right. So suppose your congestion window is 1 here, you would get back an acknowledgement after 1 round trip time, and that would make you double the window size. Then you send out 2 packets. You're allowed to send out 2 packets in flight. And then the window size increases by 4 and so on. So let's draw that out. So this is the sender and this is the receiver. So initially we are only allowed to send out 1 packet. So this is an MSS, 1 MSS which you sent out, and this is the ACK which comes back. So the congestion window is 1 maximum segment size here. So here congestion window becomes 2 MSS. We are allowed to increase it by 1, which means that we can send out 2 segments, each of size MSS. Now each of these sends back an acknowledgement. So what's going to happen when this acknowledgement comes back? Congestion window is going to become equal to 3 MSS. So how many packets do we have outstanding? This packet we've got the acknowledgement, so this one is outstanding. We haven't yet got back the acknowledgement, but we are allowed to have 3 packets, 3 MSS amount of bytes outstanding. So what would we do here? We would send out 2 more packets. Okay, and then we've hit the limit of 3. And now when this acknowledgement comes back, congestion window is increased to 4 MSS. Okay. So how many packets can I send back? Can I send out now? So this packet which was still outstanding, I've got an acknowledgement for. Okay, and now what I can do, I've only sent out 2. There are 2 MSS outstanding, so I can send out 2 more, so that effectively I have 4 MSS outstanding. Okay. So this is how it would work in practice. I send out 1, I get back 2 acknowledgements. When each of them comes back, I increase my congestion window and I send out as much as I can. So here I'm assuming that the sender has a lot of backlog from the application, lots of data available to send, and so it would send out data in this fashion. So we see that we are increasing the window size aggressively initially. So in this situation, seen over here, we start out with 1 MSS, but then we are exponentially increasing our data rate. So within a few round trip times, we will end up sending at a very high data rate, okay, of could be gigabits per second. Okay, maybe in a few seconds, maybe a few tens of seconds. In this particular case, the round trip time is higher. But of course, if the round trip time was lower, you would reach this 10 gigabits per second much faster. So, I mean, when you're doing a download, you will see you'll see TCP in action, right? You might see a slow download sometimes, but sometimes you see a fast download. So it all has to do with TCP, and it depends on the conditions in the network. It's varying its window size and so on, so that it can transmit as soon as possible. But if there is a packet loss, then maybe it will decrease the window size and go slow. So these are some of the principles that we follow in TCP, and the question is, when do we stop this exponential increase? So first of all, before we get to that, we need to say what this is called. So since we start with a small window size, this is called slow start. So we start here, but this entire phase, this exponential increase, is given this name, which is somewhat of a misfit. It's true that we start at 1 MSS, but after that we are very aggressively increasing the window size. But this whole procedure where you start small and then you increase aggressively is called slow start. So we start with this slow start, but then we want to at some point say enough is enough, we've become too aggressive, and then we switch into the AIMD mode. So what we will see TCP is doing in practice is that we start slowly. So it looks something like this, slow start, and there is some threshold which is called the slow start threshold, or SS thresh, some people called it. In the papers or the RFCs, you will see this. So after the window crosses this SS threshold, we go into the AIMD mode. Okay, so you detect packet loss and you decrease drastically. So this is normally what various TCP protocols implement. So first slow start, but then you have some threshold, which is some parameter set in your protocol. Now initially, of course, there is some value set by the OS, but after some time, after you learn more about the path, you will change this SS threshold. Okay, so once the window crosses SS threshold, you go into AIMD, and this phase is called congestion avoidance. So we want to avoid congestion, so we slowly increase, and if there is a packet drop, then we drastically decrease the window size. Okay, so this is the slow start phase, and this is the congestion avoidance phase. So different TCP flavors will do slightly different things. You know, maybe the initial window may be set differently, or this SS threshold may be set differently, and so on. But for a long time, TCP, this was what TCP used, and of course the latest versions do something more tricky. They do have something sort of a slow start here, but they slow down a little bit before this SS threshold. And if they find that there is not much congestion even when I'm at the SS threshold, then they would drastically increase. There's something called TCP cubic, which Linux at least uses. I think by default it uses TCP cubic. But TCP cubic is, I would say, more aggressive than this protocol which I've shown here. So we won't be studying TCP cubic in this course, but you can look it up if you're interested. So what is an RFC? Since I mentioned that, RFC stands for request for comments. So anybody can write an RFC for a particular protocol, and usually the TCP protocol or other protocols, the standards are actually defined in these RFCs. Somebody who's an expert researcher writes down what TCP should do, what every implementation of TCP should do. right? And the RFCs have various numbers, so you can look up RFCs for TCP and so on online. So we'll look at exactly what TCP Tahoe, Reno do, and we'll talk about TCP Vegas too in the next lecture.